everyone, today I'll be discussing the Klever wallet security incident which happened earlier this year in July 2023. Klever wallet is an app that you can download from the Apple Store or Google Play, and you can use it to hold your crypto such as Bitcoin, Tron, and Ethereum. And you can also do many other things with the app, but I won't be discussing that today. So what happened on July 12, 2023? Users started to notice unusual unauthorized transactions in their wallets, and they were really concerned because essentially their coins were being stolen from their accounts. And Klever, of course, was also very concerned because as a service that provides a wallet, they really need to make sure that they secure the coins, or otherwise no one's going to use the app, right? So how did this happen? After a day of investigation where Klever paired up with security firms and really did their due diligence to figure out what's wrong, they figured out that it was due to a low entropy mnemonic used to generate private keys, which was attributed to the BIP39 implementation of the random generation algorithm. Let's dive into what that means and why Klever, in a way, was actually not completely at fault. In Bitcoin, you have a private key and a public key, which are created using asymmetric encryption. In a nutshell, if you want to have sole ownership of your Bitcoin, you must have access and sole access to your private key. Your public key, which is derived from your private key, is where people can send you money. If an adversary were to get a hold of your private key, they can essentially sign transactions under your name or send Bitcoin to their own wallet, and you will lose your funds, unfortunately. So a private key in Bitcoin is essentially a random 256-bit number, and that means that it is 256 binary digits, so it kind of looks like this, just very long. In programming terms, this is usually done by feeding a large string of random bits, which is derived from cryptographically secure source of randomness, into the SHA-256 algorithm, which will give you a 256-bit number represented in hexadecimal form. So this is a SHA-256 online tool. It will run your input through the algorithm and give you the corresponding hash. This algorithm is just a cryptographic hash function, and it takes the input and produces a fixed deterministic output, which is that hash that you see there. So let's try to use it and see what happens. So I'm just gonna write here. So in this box, you can really input anything. You can put an entire book in there. You can put this sentence, you could put this sentence, and it will give you a hash value that is always the same amount of numbers, which is 256 bits. This is just a hexadecimal representation of it. If you see here, I will change one letter and the hash will be completely different, which is great for authentication purposes and also to keep your private key secure. Alright, so if we go back to the PowerPoint, you will see that you have to feed a large string of random bits into the SHA-256 algorithms. These have to be cryptographically secure, so you really shouldn't put just something casual like this. You should really be smart about what you put into the SHA-256 function. In 2013, a Bitcoin improvement proposal was implemented called BIP39, and this is essentially a protocol for deriving a mnemonic sentence, which is usually 12, 14, or 24 words, from a binary seed for ease of use. This is an example of a mnemonic sentence, and instead of having to write down this long alphanumeric thing, you can just write down these words and it'll represent a 256-bit number. So how does BIP39 work? I'm going to show you with an article from Medium. So in this article, they've chosen 128 bits of entropy as opposed to 256 bits. And as you can see, this is the binary digits. Bum, bum, bum. Then you generate a checksum. The checksum in this case is 128 divided by 32. So you get 4 bits, and in this case they assumed it's 0110. So you append that to the end of the number, which is over here. And then you're going to split it into groups of 11. And as you can see, there's 11 groups. And then you're going to convert it to decimal, which means that you're going to get a number such as this. It's a decimal representation of the binary number. What you're going to do is you're going to use this number as an index to the word list, and the word list can be found here. Let's see. This is GitHub. So these have been carefully chosen. And if you can see now, this is the mnemonic. The index for 49 was alert. And there you go. There you have it. The problem can be traced back to this command, bxseed, which is a command that is part of the LibBitcoin Explorer, which is a command line tool for working with Bitcoin. And that's part of the LibBitcoin toolkit, which is a set of cross-platform C++ libraries for building Bitcoin applications. And so the problem with this command bxseed is that it generates a private key based off of an initial set of entropy that is derived by the Mersenne twister, which only uses 32 bits of entropy. So that essentially means that it only uses 32 0101111s, which, if we do the math, is actually really easy to brute force. So 32 bits of entropy, oh my gosh. So sorry, this little icon is saying, oh my gosh. And you power 2 to the times of 32, because 2 is either 0 and 1. And then you get, what is that, 4 billion and whatnot guesses, which is actually not that bad. Takes less than a day to crack. This number is completely different from the number that you would get if you were using 256 bits. That number is like 50 numbers long, way harder to crack and brute force. And yeah, this is essentially how people were stealing money from different users and different wallets, because they had imported their private key that was initially created by this bxseed command, and well, you know, it didn't really work out for them. Klever was clever enough to figure that out within the day, and they told their users, like, hey, you know, you should essentially just upgrade your private key. You should either transfer your funds or upgrade to a service that they provided. And they did a really good job at really controlling the situation. And like I had mentioned, it really is not their fault. But in a way, I guess these types of applications could create some sort of security system where they would look for the entropy of incoming or like imported private keys, but I'm not sure how complicated that would be or how much money that would cost, because apparently there are ways you can measure for entropy, so that would be interesting or something else to research. But thank you so much, and I hope you enjoyed my presentation.